This unit we're going to be getting into two-dimensional kinematics. So we know that it's going to be twice as much fun because we have twice the number of dimensions. Ha ha. When we're dealing with 2D, that means we'll have motion that's either, maybe there's some motion to the east and some to the north, or it could be some horizontal, some vertical, but all the motion will be happening in a plane, in a flat surface. In one dimension, we had these are the 5 equations that we use to solve problems. We have the definition of velocity, definition of acceleration, June's or Martin's equation, depending on which class you're in, the time-dependent equation, and the time-independent equation. Now, all of these equations still apply in 2D kinematics. Again, for all the problems we will be doing in this class, we will have constant acceleration. These equations apply for constant acceleration. But they'll just apply twice. We can write them once in the x direction. This is one set of equations would all refer to the x component of motion. So all these vectors then will have an x component, and then they can also have a y component. Time is a scalar, so it doesn't have components, it's just time. And we can use any of our 5 equations in both directions. Now, practically speaking, there are a few that we won't really use a whole lot, and I'll explain why that is. But any of our equations apply in both directions. Now, because we're dealing with 2 dimensions, that means we're going to have to worry about vectors and components and all that stuff. So just a quick reminder, if we have a vector r with components x, y, then the magnitude of that vector, which you write like this in vector notation, but if I had to say this vector was velocity, and I am asking you for speed, which is the magnitude of velocity, we use Pythagorean theorem with the x and y components to find the magnitude of that vector. To find the direction, the angle, we take the inverse tangent of the y component over the x component, and as part of that, we have to give some kind of direction. So we have to say above the horizontal, below the horizontal, east by north, west by south, depends on what the problem is, but we give the angle and some kind of description of where the angle is located. And again, a reminder to go the other direction. If we are given a magnitude and direction, we find the x component of that vector by taking the magnitude times the cosine of theta, the y component by taking the magnitude times the sine of theta. This is assuming that theta is an angle from the horizontal. And then, the x, when you know where the angle is, you can determine what sign, S-I-G-N, positive or negative sign your components should have. If it's west by north, well, we usually call north and east positive, so west by north means the x component would be negative, the y component would be positive. If it's below the horizontal, then the x component we would call positive, horizontal, and then below the horizontal, the y component would be negative, it's going down. So you give the sign to those components based on where they ought to be. For today, we're going to be dealing with a special case of 2D kinematics. Actually, a lot of dealing with 2D kinematics, we're going to be dealing with projectiles, which are objects flying through the air. Well, not flying, but thrown or fired or kicked or whatever. Objects moving through the air. And mostly that's going to be on Earth. If an object is on Earth moving through the air, its acceleration would be 0 horizontally, because there's nothing pushing it horizontally, and 9.8 meters per second squared downward. So this is an example of free fall. I mentioned this briefly when we were doing 1D kinematics, that projectile motion is in free fall because gravity is the only thing causing our projectile to accelerate. Yeah, and this simplifies a lot of our equations. So if our acceleration, the x component of our acceleration, is 0, now a lot of these equations we can write in the x direction become pretty trivial. If our acceleration is 0, our change in velocity is 0, this equation becomes 0 equals 0. This equation, if our acceleration is 0, v naught and v final are the same thing, so this just becomes 2 times velocity times a half. We get delta x equals vx times time, which is the same thing as this equation. These two become the same thing. Again, if acceleration is 0, that goes away. We're left with just delta x equals v naught x times time. And if acceleration is 0, this is 0, v final and v naught are the same thing, so this equation becomes 0 equals 0. So in the case of projectiles, in the x direction, we pretty much only ever use this, because the acceleration in the x direction is 0. So that makes it much simpler. In the y direction, well, we pretty much use any of these equations. We don't often use this one or this one because in the case of a projectile, we know the acceleration all the time. And if we know the acceleration, it generally makes more sense to use one of the equations where we have acceleration. So for the most part, you'll be using one of these 3 equations. So when we're dealing with projectiles, our equations become a lot simpler. Now, something that I didn't tell you, but is sort of apparent when you look at how these equations are totally separate. And you notice in our y equations, it doesn't matter what's going on in x. In our x equations, it doesn't matter what's going on in y. The 2 directions of motion are independent. The x component has no effect on the y component. The y component of motion has no effect on the x component, as long as we are in free fall. So once an object hits the ground or whatever, then that's not true anymore. So once it reaches 0 height, then there is friction and stuff that is acting on the object. But for as long as it's in the air, the x and y components have no effect on each other. So one of the classic physics questions that's in almost every textbook, they take something like, I fire a gun horizontally, there's the bullet flying out of the gun, puff of smoke. Okay. Bullets flying out of the gun horizontally. I fire this bullet horizontally at the same time as I drop a second bullet from the same height. Which hits the ground first. All right. Now, anytime I ask a question in one of these videos, I want you to pause, think about it, and try to answer it yourself before you look at what the answer is. So think about that for a second. Pause your video, come up with an answer, and then look at what I say. Now what I have just said, so we've got the bullet flying horizontally, we've got the other one that's just dropping, and gravity will pull it straight down. Well, I just told you the 2 components of motion are independent. So even though this has a velocity in the x direction, in the horizontal direction, its initial velocity in the y direction is 0 in both cases. In both cases, you have the same change in y, we're going from some height to the ground, and in both cases we have the same acceleration, 9.8 meters per second squared downward. So, if all these are the same, we can look at the time-dependent equation in the y direction. This is the same, this is 0, this is the same. Well, that means that they're both going to take the same amount of time to hit the ground. So it doesn't actually matter. You could fire this gun, you could throw something horizontally, doesn't matter how fast it's going. If you've got a flat surface underneath you, they're going to hit the ground at the same time, which is kind of surprising, I think, but just drives home the point that these two components of motion are independent.